Alright, welcome to today's lecture. Today we're going to sort of look at a few more IVPs and sort of look at IVPs where we have sort of these piecewise functions, like the example you're shown here. So first step we really need to do here is rewrite this piecewise function as a sum of heaviside functions so that we can then take the Laplace transform. So we can go ahead and just sort of use our formula, which is, for our initial term, we can just write a 3, because that's our starting point, and then for the next term, we just do that function minus the previous one. Okay, so now let's rewrite our equation. Y prime plus y equals 3 plus heaviside starting at 4, 2t minus 8. We're now going to go ahead and just take the Laplace transform of everything. So here we're going to have s squared times capital Y. Our starting position is 1, so minus s times 1, and then minus 0. And that equals to the Laplace transform of 3, which is 3 over s, plus the Laplace transform of, we have a heaviside function here, so e to the negative 4s times the Laplace transform of 2t plus 4 minus 8. Sort of noting that this whole thing simplifies to just 2t, and moving this s over to the other side, we can rewrite this as s squared y equals 3 over, not s squared y, I forgot a term, plus y equals that. So s squared plus 1 times y equals 3 over s plus e to the negative 4s all times 2 over s squared. Rewriting it one more time, we can get s squared plus 3 over s, just combining those into one term, dividing by s squared plus 1, and then plus e to the negative 4s times 2 over s squared times s squared plus 1. Okay, so what we have to do now is actually sort of two different partial fraction decompositions. So we'll start here with, I guess, this one, which I'll underline this one in green and this one in blue. So for our green one, s squared plus 3 over s squared plus 1. And we know what is going to be equal to a over s plus b. We have an s squared plus 1, so that doesn't factor, so b over s squared plus 1 plus c over s squared plus 1. So here we can sort of go ahead and use kind of a hybrid approach. So if we plug in s equals 0, then what we're going to get on one side, 0 squared plus 3 equals a, 0 squared plus 1 plus b, 0 squared plus c times 0. And we can see that a has to equal 3. if we go ahead and now sort of write this out again, s squared plus 3 equals a plus b times s squared plus c times s plus a. Right, we can sort of see, well, c has to equal 0. Right, because there's no s squared, there's no s term on this side. We already know what a is, and 3 plus b equals 1, which tells us that b equals -2. Okay. Doing the other one sort of very, very similarly, we have 2 over s squared Remember, because we have this s squared term, we have to have a over s squared and a b over s. We can go ahead and sort of solve this very similarly, but what we'll get is a equals 2, b equals 0, c equals 0, and d equals -2. So going back and rewriting this in terms of our partial fraction, we have that this first term becomes 3 over s minus 2s over s squared plus 1 plus e to the -4s 2 over s squared minus 2 over s squared plus 1. And then we take the inverse Laplace transform of this, for this first term, it's not too bad. We're just going to end up with a 3 minus 2 cosine of t. And then here we're going to end up with, again, we're multiplying by e to the -4s. So we have our Heaviside function based at 4. And then we want to identify what is this equal to. Well, normally, both of these terms are equal to the Laplace transform of 2t minus 2 sine of t. And so what do we do here? Well, we do the same thing, but 2, and now because of the 4, we have to do the shift. So t minus 4 minus 2 sine of t minus 4. And that is going to be our final answer. All right. So this next one is a little bit interesting. So one thing I want to sort of note in general, it's not the most crucial thing to know, but it's something to be aware of. Remember that when we take the Laplace transform, we're taking an integral from 0 to infinity. So it depends only on f of t for t greater than or equal to 0. So even if sort of f changes for t less than 0, like if I have two functions and they only differ for some negative values, then you're going to sort of run into a problem with the Laplace transform. So for that, sometimes when we have these IVPs, we'll only really say what, if we're really supposed to use Laplace transform, we'll only really specify what the function is for positive or really non-negative t values. That said, most of the time, if you solve it, it turns out that if you can extend it in the normal way to for negative t values. That's why it's like not too crucial. But anyway, something to be aware of. So let's just sort of go ahead. What we'll do first is, again, write this for e to the t 0. And then here, we have a change at 1. And so we're going to use the rule 0 minus the previous function 4 to the et. Okay. So we'll go ahead and rewrite our function. We'll apply our Laplace transform. Because both of these are 0, this actually makes things very easy, and on this left-hand side, we're just going to end up with s squared capital Y plus 2sy plus y. Here we have 4 over s minus 1, and then minus Heaviside function starting at 1, so e to the negative s, and then times the Laplace transform of 4e to the t plus 1. Note that this guy here is the same as 4 times e to the t. So we can pull out that plus 1 as just an extra factor of e, and we'll end up with s squared plus 2s plus 1 times y equals 4 over s minus 1 minus 4e to the 1 minus s. Note I'm sort of putting this factor of e inside of s, 1 over s minus 1. Okay, so here I can actually use a shortcut. And so a lot of times you have to do the Laplace transform sort of at the same time, or you have to do two separate, partial fraction decompositions. But in this case, as we'll see, we can do it in one. So 4 over this is equal to s plus 1 squared minus e to the 1 minus s times 4 over s minus 1 s plus 1 squared. Okay, so I can see that all I have to do is find a partial fraction decomposition for 4 over s minus 1 s plus 1 squared. And then I can use that to sort of solve both parts of the equation. So I'm just going to go through, plug in, let's say s equals -1. I'm going to get 4 equals a times 0 squared plus b times -2 plus c -2 times 0. So this says then that b equals -2. I plug in +1, 4 equals a times 2 squared plus b times 0 plus c times 0 times 2. And so I get 4 equals 4a, which of course says that a equals 1. Lastly, to solve for c, I can just plug in s equals 0. 4 equals a, which is 1, times 1 squared, plus b, which is -2, times -1, and then plus c, which is times -1 plus 1. So 4 equals 1 plus 2 minus c. And if we go ahead and solve that, we're going to see that c has to equal -1. Right. So now let's plug everything back in. We get that y is equal to 1 minus e to the 1 minus s times (1 over s minus 1) minus 2 over s plus 1 squared minus 1 over s plus 1. So I want to sort of identify that this is the Laplace transform of e to the t minus 2t e to the negative t minus e to the negative t. And then just to rewrite it all again, just to maybe help you understand. So I know exactly what's going to happen here. If I take the inverse Laplace transform, I get e to the t minus 2t e to the t minus e to the negative t. I then have a minus e, a Heaviside function starting at 1. And then I have the same thing again, but I have to shift everything by, oh, that should be a minus. I now have to shift everything to -1. So times e to the t minus 1 minus 2t minus 1 e to the negative t minus 1 minus e to the negative t minus 1. And that's going to be my final answer. Okay, so watch out for opportunities like that where you can sort of reuse work and find a Laplace transform like that. All right. Reuse work, I mean, and not have to refine the partial fraction decomposition. Sorry, I don't know what's going on with my words today. Okay, so finally, sort of our last example for this video, I want to sort of revisit some mass spring systems. So we have a problem which is as follows. So a mass of 2 kilograms is attached to a spring stretching at 245 centimeters. A damper is attached so that the system is critically damped. and then the spring is stretched down 1 meter and thrown down with an initial velocity of 500 centimeters per second. A bullet is then fired, hitting the mass from below at time t equals 5. The impact has an impulse of 2 Newton seconds. And then we're supposed to set up an IVP modeling the scenario. So there's a lot sort of going on here. But let's sort of just sort of look through, okay, mass of 2 kilograms, stretching at 245 centimeters. The system is critically damped. And I think that's all we need to start. That's all we need to do the first part. So let's go ahead. We have 2 kilograms times our gravitational constant, right? mg equals k times displacement. So 2 times 9.8 meters per second squared equals k times our displacement, but it needs to be in meters, so it's going to be 2.45. We can then go ahead and solve for k, and we see that k is equal to 2 times 9.8 is going to be 19.6 divided by 2.45. And if we plug that into our calculator, we see that k is equal to 8. Okay, so sort of looking back, we know our mass. We don't know what our damping coefficient is, and we know our spring constant is 8. Okay. We're told, though, that the system is critically damped. So remember what that means is that c squared equals m times k. Sorry, c squared equals 4m times k. That's right. So c squared equals 4 times 2 times 8. So that's 8 times 8, 64. C equals the square root of 64. Remember, we do want the positive version. And so C equals 8. Okay. So we've got that. Now let's go back up and identify the rest of the parts. So the spring is stretched down 1 meter and thrown down with an initial velocity of 500 centimeters per second. So that should be our initial conditions, right? We should have y of 0 equals 1 and y prime of 0 equals 500 centimeters is 5 meters. Bullet is fired and it hits it from below, and the impact has an impulse of 2 Newton seconds. Okay, so I think we can go ahead and just set up our IVP. Right, we're going to have 2y prime plus 8y prime plus 8y. It hits it from below, so it's going to send it upwards, which means it's going to be a negative impulse value. So negative 2 at time t equals 5, so t minus 5. And then our initial conditions are y of 0 equals 1 and y prime of 0 equals 5. All right. So your exercise for this video is to just go ahead and solve this initial value problem. So pause here, give it a shot. And all right, So I'll just sort of start to make sure it's been a bit. So right, we should have gotten, when we took the Laplace transform, 2 times s squared capital Y minus s times 1 minus 5 plus 8 times sy minus 1 and plus 8y equals negative 2 e to the negative 5s. So we get 2s squared plus 8s plus 8 times y equals s plus 10 plus 18 minus 2e to the negative 5s. Okay, so we go ahead, do a little bit more work, and we should get our final answer is y equals e to the negative 2 t minus 5 times t minus 5, Heaviside function starting at 5, plus 7t e to the negative 2t plus e to the negative 2t. Right, and we'll end it there.